Hey everyone, this is a video lesson that I'm using in my AP Calculus AP class, and I'm putting it online in case it would be helpful to others as well. There is a link in the description of this video to a printable set of guided notes that you can use to follow along with the problems that I go over. This is one of my favorite sections of the year to teach, and I know I say that all the time, but it's always true. I was really looking forward to making this video today, so let's jump right in. Okay, the first question that we see on our set of notes is what distinguishes calculus from algebra? And that's a pretty loaded question. But for our purposes in this section, which I think I was so excited I forgot to say the name of the section, we're doing related rates here. This website has a pretty nice answer. Now, I will link this website in my Google Classroom in case you want to see all of this. But right here, okay, this is what I want to take out of it right now. Calculus takes regular rules of math and applies them to evolving problems. I love that sentence, and I think it applies very nicely to what we're going to talk about with related rates. Okay, before we talk about any related rates examples, I'd like to do a review problem where we are going to review differentials from the last section. Okay, so consider a sphere of radius 10 centimeters. If we change the radius by 1/10 of a centimeter, how much does the volume change? Okay, keep in mind that technically you do not need calculus to answer this question. You can find delta V, which is the true change in the volume, by finding the volume of the sphere at radius 10 centimeters, finding the volume of the sphere at radius 10.1 centimeters, and just subtracting, right? However, we can use, and this is what we learned in the last section, we can use what are called differentials to approximate that change. And as we move through the rest of the problems in this section, I think you'll see why that's going to be helpful. Okay, so the volume of a sphere is 4/3 pi r cubed. And again, what I want to review here is how do you use a differential to approximate the change described in this problem. Okay, so we can take the derivative of this volume formula with respect to r. We'll write that as dv over dr. Power rule here gives us 4 pi r squared. And this is one of those cool things again. The volume formula for a sphere, when you take its derivative, you get the surface area formula for the sphere. Isn't that neat? Okay, let's solve for dv to put it in our differential form. And now we will take the radius to be 10 centimeters and the change in the radius dr to be 1/10 of a centimeter. And that gives us 40 pi. Cubic centimeters, or like approximately 125.66 or something cubic centimeters. And remember, that's not the exact change in the volume, but it's a pretty good approximation of the change. If you want to calculate delta V and compare just to see how close this is, you can. I'm not going to take the time to do that in this video, though. Okay, so if you can calculate delta V, the question is, why do this? Why have this differential approximation? Well, one of the answers to that is that it allows us to do something like this. Take a look at the new problem. Suppose the radius is changing at an instantaneous rate of 0.1 centimeters per second. This is possible if the sphere is a soap bubble or a balloon. Think about it blowing up. The radius changes, everything, all the measurements change as that bubble or balloon blows up, right? We are to find the rate at which the volume of the sphere is growing. Okay, find the rate at which the volume of the sphere is growing. What we're going to do is we are going to take the derivative again of V equals 4/3 pi r cubed, our volume formula. But this time, we are going to take the derivative with respect to time. So you're going to see this look almost exactly like what we just did in the differential problem, but everything is now with respect to time. So the derivative of v with respect to time is dv over dt. The derivative of 4/3 pi r cubed with respect to time is 4 pi r squared dr over dt. This is like implicit differentiation. If you're not taking a derivative of a t variable, you need to multiply by a d, whatever variable it is, dt. Okay, and now we will take again an original radius of 10 centimeters from the original scenario. And now the dr dt is the rate at which the radius is changing, and that is 0.1 centimeters per second. Now notice we get the same answer, right? dv over dt equals 40 pi. But our units are different. It is cubic centimeters now per second. And there's our answer. And we just did our first related rates problem. Fun, right? Okay, so here's the steps for related rates problems. We didn't draw a picture in the last one that we did. You don't always have to draw a picture, but sometimes it's helpful, as you'll see with the next example. And I think that before we talk about all these steps, let's take a look at the next example and then work through the steps listed here. Oh my gosh, okay, there's a lot here. Example 1. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 of a mile north of the intersection and the car is 0.8 of a mile to the east, the police determine with radar that the distance between them and the car is increasing at a rate of 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of the measurement, what is the speed of the car? That's a lot. Okay, remember, we are going to work through these steps to try to answer that question. The question again was, what is the speed of the car? Meaning the speeding car. How fast is it going? Okay, step 1. Start with something easy. Draw a picture. Hopefully that's easy. Okay, keep in mind, you have a right angle. That's a pretty important thing to note here. A right-angled intersection, and we're talking about like north and east. Okay, so, I mean, you could get really fancy with your drawing if you want to. Sometimes I like to just have students read over this problem and, sketch it out. And I love walking around and looking at their beautiful pictures. They're always so much better than mine. I'm going to draw a right angle, and I'm going to draw a little box right here for the police cruiser because they are north of the intersection. Here's the intersection. And I'm going to draw a little box over here for the speeding car, and I put it here because they are east. They have turned the corner and are moving east. So here's our police cruiser moving in this direction. Here's the speeding car moving in this direction. And at some point it says the police determine with radar that the distance between them and the car is increasing at a rate of 20 miles per hour. Why can they do that and not just determine the speed of the car? Because then we won't have a calculus problem. So that's why. The distance between them and the car is right here. Okay, it is the diagonal. And look at what we just made. We made a right triangle, right? Let's label the sides of a right triangle with things like A, B, and C. Does that look familiar? You'll probably figure out what formula we're going to need to use here. Okay, but let's not get too far ahead of ourselves. Oh, by the way, maybe I should look at my answer. Make sure I'm not missing anything. Okay, so we drew a really nice picture. That's good for me. That's a nice picture for me. Next, write down known information. Use derivative notation if it is a rate. Okay, we have a whole bunch of numbers to work with in the problem. And what I want to do now is I want to assign those numbers to variables, right? We have some variables started over here. What I like to do next is I like to identify what I call like a little information bank, a bank of information, like some stuff that we know. So our variables are A, B, and C, right? But all of those variables are changing. The police cruiser is moving toward the intersection, which actually means A, the value of A is decreasing. The speeding car is moving away from the intersection, and that means the value of B is increasing. Okay, also, it told us that the distance between the police cruiser and the car is increasing. And so that means that C is increasing as well. It's getting bigger. Okay. Since all of these variables are changing, that means that they all have rates. And you're going to identify the rates with respect to time as variables like dA over dt, dB over dt, and dC over dt. Okay, so now let's try to fill out some of this information. The cruiser is 0.6 of a mile north of the intersection. This cruiser is 0.6 of a mile north. That's your A value, right? The other car is 0.8 of a mile to the east. That's your B. It doesn't give you a C value. It doesn't say how far apart, the police cruiser and the speeding car are, along this diagonal. But we can figure that out, right? If we know two legs of the right triangle, then we can find the hypotenuse very easily with Pythagorean theorem. So a squared plus b squared equals c squared, filling in this information and solving for c. Or just using a Pythagorean triple, 3, 4, 5, 6, 8, 10, 0.6, 0.8, 1.0. That's C. Okay, that is not what we were trying to find here, but it is something that you're going to need. So if you ever come across something that you don't know that you think you probably will need in the problem-solving process, you can go ahead and find it. I call that a little side calculation. Okay, now, how about these rates? We have more information here, right? The distance between them and the car is increasing at a rate of 20 miles per hour. I did not put the 20 for the C value because it's not the miles that are between the police cruiser and the speeding car along this C diagonal right now. It's the miles per hour that distance is changing by, and that makes it the rate at which C is changing. Okay, the police cruiser is moving at 60 miles per hour. We used A for our police cruiser length, so that is going to be our dA over dt value. Finally, what is the speed of the car? That's asking you to find the dB over dt value. And by the way, that's the next step here. Write down what you are looking for. I used to make my students write a find statement, but lately I've just been having them do this. Put a box around what you're trying to find so that once you get the answer, you fill it out, it's already boxed. So right here, this is what we're trying to find. All right, let's take a look at that next step. Write an equation to relate the variables. So what you want at this point is an equation that has all of the different variables that you need. For this one, we're going to go with Pythagorean theorem, right? A squared plus b squared equals c squared. Sometimes this is the really tricky part, trying to figure out what one formula can you use that relates all of the parts, okay? Sometimes this is the difficult part, but it won't be for this example. Differentiate both sides with respect to t. Okay, differentiate means take a derivative, right? With respect to t just means if you are taking a derivative of a variable that is not t specifically, you need to use implicit differentiation and multiply by the d whatever dt for that variable. So it's like this. The derivative of a squared is 2a. That's power rule. But we need to multiply by a dA over dt. Plus, the derivative of b squared is 2b. dB over dt. And finally, the derivative of c squared is 2c dc over dt. All right, you've gotten pretty much through all of the possibly tricky parts of this problem-solving process now. What we're now ready to do is plug in known information and solve for our unknown. Okay, we only had one unknown, so that's good news. We can fill out 0.6 for A, 60 for dA over dt, 0.8 for B. dB over dt is our unknown, so it stays a variable. And we already found out from a little, side calculation, some mental math here, that C is 1, and we were given that dC over dt was 20. Okay, from there, solve. This is 72. This is where I start to get nervous because something bad's going to happen. I hope you're not mad at me. Okay, finish solving from there. Subtract the 72. Do you see what's going to happen? Divide. I'm not going to even write that out because something bad's about to happen here, everybody. Negative 32 divided by 1.6 to solve for dB over dt. It gives you negative 20. Why is that bad? Well, remember, this is a speeding car. And it's going negative 20 miles per hour. I mean, negative could just indicate the direction, but 20 miles per hour? No. And actually, the negative is not okay either. And here's why. The distance, that the the speeding car is from the intersection, that distance B, it is increasing as the speeding car drives off. So it shouldn't be a negative number. So what do we do? Don't be mad at me, but I purposefully misled you because I like for you to see that mistake, to try to remember something that you need to be able to do when setting these problems up. And that is, okay, I don't think I have it written here, but we should put it here. We said use derivative notation if it is a rate, but also you should think about the sign for every rate. Think about signs, we'll say. Meaning, it told us that the distance between the car and the distance between the police cruiser and the car was increasing at a rate of 20 miles per hour. So this 20 should be positive. However, it said that the cruiser was moving at 60 miles per hour, but we already said that really that value of A is decreasing. So technically, we should assign that 60 to be a negative 60 miles per hour to show that it is decreasing. Negative 60. Right there in our calculations is all we need to fix this. Okay, so good news, you don't have to erase everything. What was this? This was 72, so now it's negative 72. Yeah, this was 40. That is a 6 right there. It looks weird. There we go. We're going to now add 72 and divide by the 1.6. What's that? 112. Take 112 divided by 1.6 and we have the speed of the car, 70 miles per hour. Which makes a whole lot more sense, right? Oh, look, I boxed it there, and I have it boxed over here. dB over dt equals 70. Yay. Okay, so with so many different parts changing, you can't take that delta approach to finding a change. There's just too many different variables involved. And so that is why, in the last section, we talk about differentials to approximate change, because it allows us to move on to apply derivatives to rate situations like this. All right, so that was a pretty long problem. The next one is a U-try, and as usual, when we come to a U-try, I suggest that you try it, and then I'll give you the answer. This one is not as long at all. Okay, just so you know, what we have here is just a circle with radius r. The radius is changing by 1 millimeter per second. That's how you should interpret what's going on over here. Okay, the radius is currently 20 millimeters, but again, it's changing by 1 millimeter per second. You are to find the rate of change of the area. And here is the answer. I started with my area formula for a circle, area equals pi r squared, took the derivative with respect to time implicitly, and filled in the given information. Okay, this time we didn't really need a bank of information because it was right there, but you might want to note that this 1 millimeter per second is the dr over dt value. R is 20. And we found that the dA over dt value is 40 pi square millimeters per second. 40 pi again. Just happened to be like that. All right, now let's do one that I think is super fun. Example 2. A cylindrical tank has a radius of 300 centimeters. Water is draining from the tank at 3 liters per second. The question is, how fast is the surface dropping? Okay, and we have a hint here. 1 liter is equal to 1,000 cubic centimeters. We'll want that for a conversion for the rate at which the water is draining from the tank. Okay, but first, let's draw a picture. Okay, so you're going to want to draw a cylindrical tank, a cylinder, right? Let's see if I can do this on camera. Okay, not beautiful. I have a really nice one on my, I did a nice one right there. Oh, well, whatever. Okay, and there's water. There's water in this tank at some level. And let's start to label some things. The cylindrical tank has a radius of 300 centimeters. So, you could put that right here or at the top. I'm going to put it at the bottom. Feels like it makes more sense there. 300 centimeters. And the only other number is that water is draining from the tank at 3 liters per second. Now, let's use 3,000 cubic centimeters per second instead of 3 liters per second, right? And hopefully by the units here, you can conclude that that is the rate at which the volume is changing, right? So that is your dV over dt value. Now, before we write all of that out, maybe we should think about our volume formula for a cylinder. So I'm doing my steps a little bit out of order here. Let's think about the formula that we're going to be using. V equals pi r squared h. Okay, there's our formula. But one thing that you want to try to do, especially with this problem, is ask yourself, are there variables in the formula that aren't actually variables in this situation? Okay, and in particular, I'm talking about the radius. The radius here, okay, here in the formula, it's a variable, but think about it. As that water goes down, right, the water's dropping, the water is going out, it's draining. The radius of the water is staying constant, right? It's staying 300 cubic centimeters throughout. And so that radius is not really a variable. We should not write it, I'm looking for my eraser, as r squared h. We should write it as immediately 300 squared h. 300 is a constant here. And so for our little information bank, we're not going to have an r, and we're not going to have a dr over dt. That's the easiest way, in my opinion, to look at it. Now, I will give you another option there, and that is to say that r is a variable. and have a variable r, but then you have to at some point know that the dr over dt value is 0. Okay, it makes the problem solving process a little bit more complex. I will show you that during class time at some point. But again, for right now, I'm not going to have a letter for the radius. Okay, it is a constant. I think that's the easiest way to look at it. So what are our letters? Our letters are v, dv over dt, and h, and dh over dt. Now, of those 4 variables, we only know one. We know that the dv over dt value, as I mentioned, is 3,000 cubic centimeters per second. I changed 3 liters per second to 3,000 cubic centimeters per second. Okay. I don't have any of these other pieces. Which one am I trying to find? Let's put a box around which one we're trying to find. The question is, how fast is the surface dropping? Okay. That is talking about how fast the height of the cylindrical water is moving down, right? And so that would be our dH over dt. Just so you know, what you are trying to find is always going to be another rate. So if there's only one other unknown rate, put your box around that. That's what you're trying to find. Okay, we still have 2 other unknowns. And the problem is we can't figure these out just from this little bit of given information. So we kind of just have to leave them unknown and hope that we don't need them this time. And we don't need them. Here's why. Let's simplify this formula a little bit before we differentiate it. 300 squared is 90,000, right? Pi h. There's our formula. And when we differentiate this, the v goes to dv over dt. So we don't really need a v value. And 90,000 pi h, the derivative of that is 90,000 pi dH over dt. So we don't need the h value either because it went to dH over dt. So filling in the known information is now just filling in 3,000 for dv over dt. And we are ready to solve for dH over dt. Dividing by 90,000 pi will do that, and I just reduced that fraction to 1 over 30 pi. Guys, I made a mistake. This time I didn't do it on purpose. I was just looking at my answer key and I'm like, oh, I made a mistake. Did you spot it? This is where I'd love to see if, I'd love to see your reaction in person because, yeah, I made a mistake. What is it? Remember what I said way back here when I purposely made the mistake? You need to think about your signs for your rates. The water is draining from the tank, which means the volume is decreasing. That dV over dt should be negative. Negative, and dH over dt should be negative, right? Okay, so negative 1 over 30 pi centimeters per second is our correct answer for how fast the surface is dropping. Yay. I should have said I did it on purpose, but I can't make that work. All right, next example. A hot air balloon is rising straight up from a level field tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? All right, this one is super fun because we have a picture here. So what you want to think about is that, there is a level field, and there's a rangefinder that is tracking this balloon, and the rangefinder is 500 feet from the liftoff point. So if the liftoff point is somewhere over here, we'll just go horizontally with it like that. Okay, that's 500 feet. Now, when I'm in class, I like to run around with this when I teach it. The rangefinder's not moving like this, okay? It's not running back and forth. That rangefinder is staying right there, which means the 500 feet is another constant, like we saw with the radius of the cylinder in the last example. So again, we don't need a variable for that part. Okay, the balloon is rising, the balloon's going up, right? And so this is changing, and so we should put a variable for this length, and I'm just going to use h for height. Okay, finally, it talks about the rangefinder's elevation angle, so we should draw in this diagonal. And that is changing as well as the balloon rises, right? This angle is changing, so we should have a variable here like theta. Theta is a good one to use. I'm going to put a right angle symbol right there. So this is fun because we just got to put all of that stuff into this cute little picture, right? But also it's fun because what we get to use here, should I tell you yet, or should we do our little bank of information? Maybe we should do our bank of information. Okay, what are our variables? We have theta. Theta is changing, so we have d theta over dt. We have h, and it is changing, so we have a dh over dt. What is something that relates angles with side lengths of a right triangle? SOHCAHTOA. That's what we get to use here. That is so fun. We get to use SOHCAHTOA. And not only do we get to use SOHCAHTOA, we get to differentiate SOHCAHTOA. Yes. Okay, so let's try to fill out some of this information. The 500 feet, keep in mind, that's not going to go in our little bank of information here. That is the, we could call it the adjacent side, right, of our triangle, and it is a constant. Okay, so it's not the h, it's not the theta, right, it's none of these. The pi over 4 is the angle measure. The 0.14 is the rate at which the angle is changing, so that will be our d theta over dt. So we don't have h and we don't have dh over dt. Which one should we put a box around as what we are trying to find? The question is, how fast is the balloon rising? Not how high is it, how fast is it rising? So that is dh over dt. Remember, it's always the other rate if you only have two rates involved. All right. So, something that you want to ask yourself now is, should we find h? Do we need to find h? Okay, and it's up to you if you want to do any side calculations that you can do ahead of time, or if you want to just wait and see, if you need it or not need it. So I'm going to wait and see, which means we don't need it. Okay, and here's why. We're working with the opposite and the adjacent, the opposite and the adjacent. And so that means we're going to be working with tangent. The formula we want from SOHCAHTOA for tangent is tangent of theta equals opposite over adjacent. Don't fill in values yet for your variables, but do fill in values for constants. So from here, I can say tangent parentheses theta, still a variable here, equals opposite, which is h, over adjacent is 500 and not changing. So that one can go in right away. Okay, finally, I have one other suggestion just because I know this will make things easier when we go to take a derivative. Let's multiply that 500 over to the other side. Now, here's why we don't need h. What we now need to do, we have a formula that relates all of our parts, right? we need to take its derivative. We're ready to differentiate. And the derivative of h is just going to immediately go to dh over dt. That side we can do right away. The derivative of h is dh over dt. The h goes away, so we do not need to do a little side calculation to find h. Okay, so that's why I didn't do that. The derivative on this side, not as fun, but not bad. 500 tangent becomes 500 secant squared theta. Implicit differentiation, though, says we need to multiply by d theta over dt. Now we're ready to just fill in all of our information and get our answer. Theta is pi over 4. I don't know if you can hear background noise in this video, but there's like 4 teachers standing outside of my door right now being so loud. All right, I'm going to try to concentrate. Of course, one of them is an AP literature teacher. Because he has nothing better to do. Meanwhile, I'm here teaching. All right, so we can type this all into the calculator at once. Watch this. 500 secant is 1 over cosine pi over 4. It's squared times 0.14. 140, that sounds nice, right? What are the units? It's the rate at which the height is changing. Okay, so this was given in 500 feet. So this is 140 feet per minute. The rate of change of the radius was given as a per minute value. So this is also a per minute rate. We did it. Okay. This is where I'm going to stop this video. I actually have one more example to go over, example 4, but it's kind of a longer one. It takes a lot of explanation, and I think I would rather do it in a separate video or class discussion. So again, we will stop with example 3, and as usual, I hope this was helpful. Bye.